Hello and welcome to our lesson on the cosine wave, or sometimes called the cosine curve. So this is just the name of the graph that is produced by graphing the parent form of our cosine function, y equals the cosine of x. So again, this is like the parent form of our cosine function. And I put an x there, but you can put a theta there because x, our input, does represent angles, just as we saw with the sine curve. And I'm jumping all over the place here. So the graph of our cosine wave, just like with the sine, okay, we're going to be reading the graph the same way we read the unit circle. And what we're going to look at for this graph is just one interval from 0 to 2 pi, because we know that if we rotate multiple times around, the same pattern of repeating x values in this case is going to happen. Okay, so inputs are going to be angles just like before. Now our outputs are going to be cosines of those angles. Okay, so similar concept. Actually, I'm going to move this. I'm sorry if you wrote that, but you're probably going to want to move it too because it's going to interfere with the graph. And now one more time. Okay, so just like the unit circle, when I'm reading this, I can see that a 0 radian, 0 pi radian, 0 radian, 0 degree angle intersects the unit circle at these coordinates. And when I'm looking at the x value there, I'm seeing the exact value for the cosine. So in the same way, I could say that the cosine of 0 is 1 by reading the unit circle. I can make that point in my graph at 0, 1. So that is when I input an angle of 0, my corresponding cosine is 1. And so what we're going to see is our graph start at its maximum value, and if we rotate around the circle, so again, I have all these values for cosine I could graph. I'm just not really keen on graphing fractions when I don't have to. Maybe the 1/2 isn't bad, but radical 2 over 2 and radical 3 over 2, not so much. So I'm going to skip all the way to our next value for cosine, which is 0. So at pi over 2 radians, 90 degrees, our cosine hits the x-axis at 0. And it should make sense that we're decreasing. So as we are moving along our cosine values here, what's happening is we're getting closer to 0 on the x-axis, so those values are decreasing. And then we should continue to decrease because we're going to keep going in the negative direction the farther we go this way. So again, I'm going to skip all those fractions and I'm going to end up here. And now I just want to delete this because it looks ugly. So I'm going to jump to pi radians, and I already did this one. At pi radians, or 180 degrees, our cosine value is going to be -1. So we started at 1, and then we went to 0, then we're going to -1. And then as we turn this corner, our x values are going to be increasing, cosine values are going to be increasing because we're going to be getting closer to 0 as we go this way. So I'm going to skip all of these, and I'm going to go to, again, our next nice one, 3 pi over 2, or 270 degrees, we're back to 0. And then if we go full circle, we're back to where we started, which is +1. And if we lap around the circle again, we're going to see those same y values. And if we go backwards, we're going to see those same y values. So we're just going to try to capture this one cycle, this one lap around the unit circle. So at pi is when we went to our minimum value, which was -1. So minimum x value being the farthest left the graph goes, and the maximum x value being the farthest right that our graph goes. Whereas with the sine, we had our maximum and minimum this way because that's the highest and lowest on the graph. So we are going to start at the max, hit 0, hit the min, and then 3 pi over 2 we're back to 0, and then we're going to end at the max. Now if you notice, we have all this symmetry happening and a lot of similarities happening in our unit circle. The values that we see for sine and cosine, they're all the same values. They just kind of shift around. So we see lots of similarities between this curve and the sine curve. Again, maxes being 1s, mins being -1s. We have x-intercepts, and all the things in between, the 1/2s, radical 3 over 2s, radical 2 over 2 is all the same, but not happening at the same time. So when we go to draw this curve, oops, that's my eraser. We're going to connect these, and remember, we want to make this a curve, not a V or rigid looking graph. This is going to be a nice fluid graph here. So something like this. This is what one cycle of the cosine wave is going to look like. So in the same way, when I say y equals x squared, you should be envisioning your parent quadratic function, your parent parabola with the vertex at the origin. Or when I say y equals the sine of x, you're thinking about a shape that's like this, but we start at 0, end at 0, hit 0 in the middle, and it's the maxes and mins in between the zeros. Okay, this one, cosine curve, I want you to kind of try to program the brain. Okay, what's happening with the cosine curve is the same pattern of repeating y values, but they're shifted. So cosine doesn't start at 0. Cosine starts at the max and ends at the max. Right in the middle of that, so we start at the max, we end at the max. In the middle of that, we hit the min, and then in the middle of those is when we have our zeros. So when I go to graph, those are the things I'm sort of telling myself. Then remember, this periodic function has a midline. Midline is going to be right there at the x-axis. That cuts that total horizontal height in half, and that half of that horizontal height being 1 we see as our amplitude of 1. And again, 0 to 2 pi, one lap around the unit circle. That 2 pi radians is how long it takes for that one cycle to happen, so that's going to be the period of this function. So lots of similarities to what we saw in the sine wave. So this graph again is a periodic function. Just like the sine wave, it is continuous over its entire domain. So I could follow the curve with a pen or pencil all the way forever left and right without having to lift my pen or pencil. There's no gaps or breaks or asymptotes or anything weird like that. Okay, so it's a continuous graph. Again, our amplitude is 1, periods 2 pi. We saw a maximum of 1, minimum of -1. And that makes the range of this graph -1 to 1, just like we saw before, inclusive. And the x-intercept's a little harder to see. So I want to take you off this note sheet for a second here. So we see the first x-intercept happening at pi over 2. We see the next one happen at 3 pi over 2. You could probably guess where the next one's going to be, but it would be 5 pi over 2. And I could show you in the unit circle. That's probably a good idea. So the first x-intercept is at pi over 2. Get a highlighter here. So that's happening here when we have a 0. And then the second x-intercept happens at 3 pi over 2. And then if I lap around again, so this was a half pi, and then another, every time I add pi to that, I'm going to end up back where I started. So if I go around another full pi, I end up here. Go around another full pi, I end up here. So I started at 1 pi, and then I have to add I don't know what I'm trying to say. Can't explain this very well. But so we're at pi over 2, and then I'm going to be at 3 pi over 2. Oh, because I'm sorry, the 90 degrees, right? So we're adding 90, or a pi over 2, adding another one. So that's adding 2 pi over 2. So 2 plus 1 would be 3 pi over 2. Then we're going to add another pi over 2 and another pi over 2. So then we'd be at 5 pi over 2 and so on. So I probably did not do that justice. But let me go back so I can try to explain the formula here. So 5 pi over 2 would be the next one, and 7 pi over 2 would be the next one. So if I'm trying to generalize where the x-intercepts are going to be, it's not as simple as with the sine curve where they were just at multiples of pi. So I know each of these is going to end up having a pi over 2. And remember, we're talking about the parent form. So I know I'm going to have a pi over 2 in it, but the question is what's in front of that. So with sine curve, it was just n times pi. Stick an integer there in front of pi and we're good. Now it's going to have a pi over 2, and what's going to go in front of it? So if we look in front of the pi over 2, we've got a 1 happening here, and then a 3, and then a 5, and then a 7. So that's what we need a pattern for. So think about like a table of values, okay? If you had a pattern of a 1, and then a 3, and then a 5, and a 7, and maybe even think about this as a linear function where we're moving consecutively here. The rate of change between these is 2, and the starting point would be 1. So just like a linear function where we would say it's 2x plus 1, we're going to say this is going to be a 2n plus 1 where n is an integer. So the first one, or this one for example, if we wanted to see here, if I plugged in an integer of 1, 2 times 1 would be 1 plus 1 would be 3. That's a 3 in front of my pi over 2. Or if I plugged in a 2, 2 times 2 is 4 plus 1 makes 5 in front of my pi over 2. Or plug in a 3, right? 2 times 3 is 6 plus 1 would be 7 in front of my pi over 2. So if that went way overhead, don't worry about it. just know that this is the generalized form, that 2n plus 1 in front of pi over 2, for our x-intercepts. So again, not as simple as a sine curve, but hopefully that made a little bit of sense. So we're looking at a 2n plus 1 in front of a pi over 2, where n is an integer. So any integer I plug into that little 2n plus 1, what is produced in front of a pi over 2 would be where the parent form is going to have an x-intercept. Now, yesterday when we talked about, or previous lesson, we talked about the sine curve, or the sine wave being an odd function with symmetry about the origin. Here, we are looking at an even function that's going to have symmetry about the y-axis. And let me just show you in Desmos, okay? So in Desmos, if we wanted to just verify the work we did up there, or so I can show you what it means, this evenness, although we talked a little about it last time. If I was to graph y equals the cosine of x, there's basically the picture, but remember, we want to change our scale so that it looks like, what we're dealing with on the paper. So I'm going to go on my x-axis from 0 to 2 pi, and I'm going to go by that scale of pi over 2, which is good, and then I don't need this to go so far up or down, so I'm just going to go -2 to +2, and then that gives us a good picture. So there's that same picture we just made, right? Now let me just scroll over a little bit here. If I was to continue the function, this function has symmetry about the y-axis. So maybe you can see there, if I was to fold this graph over the y-axis, those two halves would match up. Now technically, that when we have that symmetry about the y-axis is because we have this property, the same property that makes sense with the y equals x squared. Why do we have our parabola? Let me go off this for a second. Why does our parabola have that symmetry about the y-axis? Well, because when I plug in a 1, I get a +1. When I plug in a -1, I still get a +1, right? No matter whether I square 1 or a -1, I end up with the same result. If I plug in a 2, I go up to 4. If I plug in a -2, I still go up to 4. So whether I plug in a positive or a negative, my output doesn't change. So that's the resulting function here. If I take my cosine function and plug in a negative, it doesn't affect the output. I still get the cosine of whatever I was taking. And you can see that also happening on the unit circle. So if I go to plug in, or look at the angle, let's say pi over 2. Okay, the cosine of pi over 2 is 0. If I look at the cosine of negative pi over 2, it's still 0. So whether I'm positive or negative, and that should make sense here, right? If I'm positive or negative, my x value, not affected. Okay, so trying to erase, sorry. Alright, so again, the notable characteristics of our cosine wave. Now, the connection between the sine and the cosine, they're basically the same graph, and I've mentioned this already a couple of times, but they have the same max and min. They both go up to -1 or down to -1 and up to +1. Same max and mins. They both have an amplitude of 1. They both have a period of 2 pi. Again, the amplitude making sense because the max and min and the period of 2 pi, because that's our one lap around the unit circle. They have the same pattern of repeating y values. Those y values just happen at different locations. The only difference in these two curves is the starting point. Sine, we got to remember, starts at 0. So sine starts at 0. Cosine is going to start at its max, which would be +1. So the rest of it's the same. So we can see a 0, and then a 1, and then a 0, and then a -1. I can see that here too, right? I've got a 1, 0, -1, 0. They're just happening at different locations. Okay, so the only difference in these curves is the starting point. We can technically say that one graph is just a horizontal translation of the other. So imagine taking this blue one and just sliding it over. I would see this point match up here, right? This point's going to match up here. This point's going to match up here, and I could do that all the way across. So one is just a horizontal translation of the other, and that's a concept that we're going to come back to in the next topic. So one graph is a horizontal translation, and I should have made a bullet for this, my apologies. Horizontal translation of the other. Okay, but the key for graphing, again, is sine starts at 0, cosine starts at its max. Unless, of course, we're not looking in parent form. Then we could see some of these characteristics are going to change. So let's talk about the general form. Now, luckily, the same properties we talked about with the sine wave are going to happen here. So as soon as I multiply here, some things or components, characteristics of our sine wave are going to change. So if you remember from yesterday, what happens when we change a? And I can go to Desmos since I have this. So like if I stick a 5 out here, let me go back to my one cycle from 0 to 2 pi, okay? If I stick a 5 out here just as an example, what happens is my graph now starts at 5 instead of starting at 1. So my max has gone up to 5 and my min has gone down to -5. And that means that A is going to show us not just the amplitude, but it's going to show us the actual starting point. So if I put a positive 5 out there, we saw it go up to 5. If I put a -5 out there, then we know that negative makes a reflection, and in fact makes our graph start at -5. So the value for A for the cosine function shows us exactly where the graph is going to start. So when it's positive, we're going to start at the max and whatever that value is. When it's negative, we'll start at the min and whatever that value is. So A shows us the starting point of the cosine curve. Also ends up being the amplitude, the absolute value. Remember, if there's a negative, it just means we're starting at the min instead of the max. But if it's a 5, -5, +5, amplitude's 5. And B, just like with the sine wave, shows us the number of cycles that are going to happen from 0 to 2 pi. So normally it's one cycle, but if I stick, let me go back to this, normally it's one cycle in there. If I put, if I put a 2 in there, then we're going to see 2 cycles. If I put a 5 in there, I'm going to see 5 cycles. Okay, so that's going to affect how many cycles there are from 0 to 2 pi. Remember, we refer to that as the frequency over that interval. And then if we wanted to know the period, like if I had to fit 4 cycles in there, I might want to know where one's going to end, and that's what we call the period. We can always take our 2 pi and divide it by how many cycles there are, and that's going to show us when one should end. Okay? So let's practice graphing, identifying things similarly to the way we did in the last topic. So seeing that -1 there, that tells me that this graph, instead of starting at its maximum, is going to start at its minimum at -1. So that right there says this graph starts at -1. It's a reflection over the x-axis, but for the cosine curve, it's specifically telling us where to start. So if I want to graph this, let me zoom so we can see this nicely. First, let me label my axes. We're going to go pi over 2 pi, 3 pi over 2, and then 2 pi. That's going to be the standard if we're just looking over that interval. And I probably should have put the directions in there, but that's what I want. So cosine, again, here I have a -1. I'm going to start at -1. And cosine starts and stops in the same spot. So normally they both are at the max. These are both going to be now the min. So we're going to start and end at the min. And in the middle of the graph is where we hit the max this time. Normally that's reversed, but remember this one's reflected. And then in between the maxes and mins is where we have our zeros. So 0 here, 0 here, and now we can sketch this out. So there is one reflected, that looks terrible, one reflected cosine wave. I can't see where I'm going. It's a little better. So amplitude didn't change, still 1. Period didn't change, still 2 pi. Okay, just reflected over the x-axis, so every one of those outputs just flips. And again, this is something we can confirm. So if I stick a negative out here, then boom, there's the picture I just made in my paper. Okay, let's look at the next one. We know if we put a 3 out here, that's making our amplitude 3, but specifically that 3 means start this graph at 3. Starts at 3. So we're going to go pi over 2, pi, 3 pi over 2, 2 pi. Again, this time we're going to start at 3, end at 3. And then in the middle is where we hit our min. So our amplitude is 3 now. Again, we're going to start and stop at that maximum in the middle, the minimum -3, and then in between the maxes and mins is where we have our zeros. So we'll plot those, and now again we can sketch this out. And there we have it. So again, it's still just one cycle, but now we have an amplitude of 3, and it's still that one cycle that over that 0 to 2 pi interval, so the period is still 2 pi. Okay. How about this guy? So now we've got a 2. Instead of multiplying it by the function, which impacts the y, right, the vertical, now we multiply x. That's going to impact how we move on the x-axis. This is going to be a horizontal compression of the graph. This time the 2 here is going to make 2 cycles from 0 to 2 pi. And because there's still a positive 1 here, just like the parent form, we're still going to start at positive 1. So let's go pi over 2, pi, 3 pi over 2, 2 pi. So just like the parent, this one's going to start at 1 and end at 1. And let me stop there. I got to fit 2 cycles in here, okay? So instead of fitting the 1 cycle from 0 to 2 pi, if I have to fit 2 in here, think about the period, okay? And that 2 pi is now being split into 2 cycles. Remember, 2 pi divided by b, that means that one of them has to finish at pi. So now I want to start and stop here for that 1 cycle. So start and stop at that max of 1. In the middle of that, the min of -1. And in the middle of those maxes and mins are zeros. So there's 1 cycle, and I repeat that. So we got the max, in the middle, the min, and then between those, the zeros. All right. And now we connect. Easier said than done sometimes, but there it is. So amplitude didn't change, still 1. The period changed, right? We said the period was going to be pi. If I had to fit 2 of those in 2 pi divided by those 2 cycles means one of them had to finish at pi. All right, one more. So now we have 3 changes in this one. Not only am I looking at this starting at -2, I'm also looking at this, meaning we have to have 4 cycles from 0 to 2 pi. Okay, so let's go here. Need another color. Pi over 2, pi, 3 pi over 2, 2 pi. And let's go ahead and find the period. So the period, remember, we're going to take our normal interval 2 pi and divide it into 4 cycles, which means one of them has to happen in that pi over 2 length. So we're going to have 1 cycle that fits in here, and then here's the second one, and the third one, and the fourth. So all 4 of them will fit if each one of them takes only pi over 2 radians. So I'm going to get the first one in. So remember, this one is reflected and it has an amplitude of 2. So I'm starting at -2. And the first cycle is going to end at pi over 2, so I want to stop at -2 there also. In between those, my maximum of 2, and then in between those, my zeros. Now I just got to repeat that 4 times. So we have the max 0, or min, sorry, 0, max 0, min, and then 0, max 0, min, 0, max 0, min. And now the connecting of the dots. This looks kind of bad. I think it's a little easier to do on paper than here. I can't see where I'm going. My hand is in my own way. And now I'm at the end of the iPad. And make it really shaky over here. Okay, so something like this. And again, we can always confirm what we're doing, so this would be a nice one to confirm. Let's make sure we did this right. So if I put in a -2, and then I put in a 4 in front of my x, there's the picture we just made, right? We see all those, let's see, we got 4 peaks on both sides there. Yep, starting at -2, ending at -2 at 2 pi. Yeah, so the graph looks good, okay? So this is the goal, right? Know where sine starts, know where cosine starts, know what the amplitude is going to be, when does it reach the maxes and mins, when does it reach the zeros, and then be able to identify all that information so that you can sketch the graph. So ideally you're graphing everything by hand and then confirming your work with technology. Remember, when we take our quiz over this module, that's going to be a non-calculator quiz. So do your best to get fluent with doing this by hand, but by all means, while you're learning and practicing, confirm what you're doing with the calculator. Okay? So let's work in reverse in these last 2 examples. We have the picture, we're just trying to write an equation. So we know these are cosine curves and not sine curves because they're not starting at 0. One starts at the max, one starts at the min. And that starting point is telling us a. So here, for example, that tells me that a has to be a -1. And then if we're thinking about the full cycle, for full cycle we would have start at the min, end at the min, we'd hit the max, and then we'd have two zeros in between. So we would have the peak and then the other half right there, right? So like the one half of the hill, then the other half. But notice in this picture, we got the 1 0 and we got to the max, but we don't turn back and hit the other 0, go to the min. So I'm only seeing half of a cycle in here. So that half of a cycle tells me that b has to be 1/2. And so our equation is going to be y equals negative cosine of 1/2 x. Alright, and then here, excuse me, so here we have our starting point, and that is midway in between 0 and 1. So that point right there is telling me that a has to be a half. That's the amplitude. It'll only go in a half a unit up and a half a unit down. And then let's think about this. If we start at a max and end at the max, there's one cycle. And then over here is where we're going to get to our second cycle. And then we're going to loop around, and boom, there's going to be our third cycle. And I can even highlight for you there. So there's one. Remember, start and stop in the same spot. And then there's a second one, start and stop in the same spot. And then here's a third one, starting and stopping at that maximum. So 3 cycles in here means b has to be 3. So for our equation, y is going to equal 1/2 times the cosine of 3x, or 3 theta if you like that variable better. And just for good measure, let's go ahead and double check. Okay, if I put a 1/2 here, and I put a 3 here, is that the picture that I'm seeing on the paper? Yes, looks good. Okay, so be able to read the graphs, be able to read the equations, be able to produce the graphs, be able to verify everything you're doing in Desmos, and you should be good to go for at least our sine and cosine waves, and then we're going to add on the other trig functions as we move along. So that does it for this one. If you have any questions, reach out. Until next time, take care.